Now students, we start our course and we start with the definition of the differential equation. So in order to understand what is the differential equations, let us start with what is equation. For example, we have an equation in one variable. You know the answer, that x is equal to 2. For example, if we have one power of variable, then we have one value for the variable. If we have, for example, power 2, then we have x is equal to 2 values of x. So depend on the power on the variable, we have the values of the equation. This is an algebraic equation. And we have discrete values. If we talk about the differential equation, then a differential equation So, in contrast with algebraic equation, in differential equations we have the derivatives, and the derivative could be one or more unknown functions or dependent variable with respect to one or more independent variables, and this equation in that form is called as the differential equation. In contrast with algebraic equation, the solution of a differential equation is a function. For example, y of x or some function phi of x. So this is the dependent variable, this is independent variable, this is dependent variable, this is independent variable. We have seen that in algebraic equation we have some discrete values, but if we solve a differential equation we get a function. So this is the definition of differential equations. Now we will remove our confusion between ordinary differential equation and the partial differential equations. So we start differential equation and we categorize it. How do we categorize? For example, we have several kind of differential equations. If we want to arrange them, then the first thing we will see, we can classify it by type. So if a differential equation contains the derivative of one or more dependent variable with respect to only one, this is important, independent variable, then it is called the ordinary differential equations. For example, we have a function u and we differentiate it with respect to only one independent variable. Then this equation, this differential equation will be called ordinary differential equation. In contrast to this, if a differential equation contains derivative of one or more dependent variable with respect to more than one independent variable, then it is called partial differential equation or PDE. Example is, in the same differential equation, the function u can be differentiate with respect to t, and another one, for example, with respect to position, with respect to time, with respect to position. In order to differentiate in the equation, we can understand what is ordinary differential equation, what is partial differential equation. In partial differential equation, we do not use simple d. We use a curly special d, like so. This d is for ODE, and this curly d is for PDE, partial differential equation. So this is one of the difference between ordinary differential equation and partial differential equation, that if the independent variable is 1, only it is ODE. If it is more than 1, then it is PDE, partial differential equation. And this is only one of the notation, d upon dt, and we call it dawa. Usually we read it as dawa upon dt, dawa u upon dawa t, for example. So this is the classification by type. Just a moment, as we have already studied the differential equation course in previous semesters, so this course is about the partial differential equations. So I want to make you understand the difference between ordinary differential equation and partial differential equation. From this moment, we are going to study the partial differential equations only. And now we will see that if we have a partial differential equation, or we have more than one partial differential equation, how can we classify them? How can we arrange them? So an example of a partial differential equation, we can say, if we want to, first of all, we know that a differential equation is something that has, we want to know something which is changing with time or with position. If it is only changing with time or only changing with position or only one variable, then it is ordinary differential equation. If something is going to change with respect to position and with respect to time as well, then the equation will be called partial differential equation, because by definition partial differential equations are the equations which have one or more independent variable. So as an example, if we want to know the temperature of a room with time and with position as well, for example, if we have a room and we have a heat source here. So you know that the temperature here near the heat source will be greater and temperature far from the heat source will be lower. So temperature in this case is a function of position. For example, if we just one dimension, then it is temperature is a function of position. It will be different here, it will be different here, it will be different here. But if you increase the time and if you note the temperature with respect to time as well, then you will see that again with respect to time, temperature in first hour, for example, in first 5 minutes will be less, will be more or less. It can be more, it can be less depending on the situation of the room, but obviously it will be changing with time. So in that case, the temperature is both function of position and both function of time. So if we denote this temperature with U, then we can write it as function of position and function of time. In that case, if we write the equation, it will be a partial differential equation because the dependent variable can be one or more, but independent variable, if more than one, then the equation will be partial differential equations. And we use the notation, for example, as I told you that we use that notation like this. We can also write it like, so if we see this kind of notation, we can see that U is a function which is going to be known, which we are going to know this function, and it is differentiating with respect to time. For example, if I write second derivative, it will be written like this. Now we are going to see a few well-known PDEs. These are the PDEs we are going to study in this course. So first one is So these are some well-known PhDs, few well-known PDEs. Don't confuse when they are written in this form, because you are going to solve heat equation, you are going to solve wave equation, and you are going to solve the Laplace equation. But what you can understand if you see an equation written like this, that this is the standard form of heat equation. What you can see only, if this is the heat equation, the U represents the temperature. We are going to study this in detail, but this is a brief description. So if this is a heat equation, then U, general symbol, represent the temperature, and if there is a subscript T here, which means that this U is differentiating with respect to T. So we know that ut is dava u upon dava t, and this is first derivative only. Then this alpha represent a constant, and here the temperature, because this is heat equation, temperature is differentiating twice with respect to x-axis. So uxx is basically second derivative, because there are two x. If this is the single x, there would be no any power, but if it is xx, this is differentiating with respect to x twice. Alpha is a constant. When I started writing these equations, I did not write alpha, because for simplicity, if we take alpha is equal to 1, then the equation becomes like this. But if we take the value of alpha, then the standard form of the equation is this one. So this is the heat equation. Heat equation consists single derivative with respect to time of temperature and double derivative with respect to position. Since this is only in x direction or x-axis, we call it one-dimensional. Also, when we know that x, y, z are rectangular coordinates, we also call it heat equation in one dimension in rectangular coordinates system. In second equation, we have similar form of heat equation, but in this equation, heat is also spreading in y direction as well. So because of this x, y, this is the two-dimensional equation. If we add u, z, z, then this will be the heat equation in 3 dimension, and again it is in rectangular coordinate system. This one is not familiar, but you can understand that here the rectangular coordinate system is no more used, but r, theta, phi. R, theta, phi are the elements of polar coordinates. So this is an equation. We don't know what is this equation, but we can understand that this is in the polar coordinate system, and this is the double derivative of something with respect to r. This is double derivative with respect to theta, and this is single derivative with respect to r. Then we see another equation. This is the wave equation. Again, I am not explaining that what u represent, because in the next lectures we are going to see the wave equation in detail, and we will see that what u represent. But only to understand the things, since this is two-dimensional heat equation, if we add u, z, z, this will be three-dimensional equation. So this is again a three-dimensional equation, looks like this, and this is similar. What is the only difference in heat equation and wave equation? That the symbol is single derivative in heat equation with respect to time, and in wave equation it is double derivative of with respect to time. However, the u represent another thing in heat equation and u represent another thing in the wave equation. But again, if we see this equation, we can only say that this is an equation in which u represents something, but this is the double derivative with respect to t. This is double derivative with respect to x. This is double derivative with respect to y. This is double derivative with respect to z. And because all three space coordinates are present, x, y and z, this is 3 dimension. So alpha here also is the constant. If we take the alpha value 1, then this alpha will be vanished. But I just want to show you that how the equation we are going to solve can be written. This is another equation, looks like similar to the wave equation, but there are some additional terms here. For example, the single derivative with respect to u and u itself here is present. These gamma and beta are constant. Again, there is alpha. So this is again a telegraph equation, but because there is only x coordinate, you can say that yes, this is xyz, so this is rectangular coordinate system and only x is present, therefore this is in one dimension. So by looking at the equation, you can tell that what is the coordinate system you are going to use to solve this equation, how many derivative you are going to take, what is the equation, and whether it is one dimensional or it is two dimensional or it is three dimensional equation. So in the examples we have written on the board, we have to note that the unknown function u is always depends on more than one variable. In heat equation, it is dependent on the t and it is dependent on the x. If we talk about the one-dimensional heat equation, equation number 1, and the variable u which we differentiate is called the dependent variable, and the one differentiate with respect to is called the independent variable. For example, from the equation number 1, one-dimensional heat equation, u is the dependent variable, t and x are the independent variables. And in the third equation, the Laplace equation in polar coordinates, you can identify the dependent variable and you can identify the independent variable. So the u is dependent variable and r and theta are the independent variables. Now, in order to solve the partial differential equations, we have several methods, and in these methods we are going to use the separation of variable in our case. So we are going to use the separation of variable for the heat equation, for the wave equation and for the Laplace equation, and we have different kinds of situations in these equations, such as homogeneous and non-homogeneous, different type of boundary conditions and different coordinate systems. So there will be several cases for which we solve these three equations. and we use the method of separation of variables. The other method of solving the equations are integral transforms, change of coordinates, transformation of the dependent variables, numerical methods, perturbation methods, impulse response technique, integral equations, calculus of variation methods, and eigenfunction expansion. However, at this level we are going to use only the method of separation of variables, and we will see that how this method is used to find out the whatever equation you are using, the dispersion, the distribution of, for example, temperature and heat in the heat equation.